Okay, good morning. Okay. So in this morning, I believe the weather is getting colder, and maybe it will also change the gravity in your bed. Okay. Anyway, uh, while we're waiting for other students who will just come maybe in a minute, I would like to just try to finish off what we have left, partial fractions, and if we still have time, then proceeding to the next section. The next section is supposed to be the next two in your textbook is thank you, is the strategy for integrations, but I think I will just leave that for further exercise, I think next week or maybe tomorrow. And the other part is about the approximations, which is, I believe, some of the approximation we have already discussed in Riemann sum. So I just adding some parts of the approximation. And then the last one in chapter 7 will be the improper integral. So far we are integrating the continuous functions without any discontinuity, without any having any the endpoints also it's definite. In improper integral we will have either we have discontinuity or we have the endpoints that has infinite numbers. So that's our agenda for today, and I would like to remind you that I have posted a new quiz that is for chapter 5, so you could try to finish off that quiz within this week. I think the deadline, so the link will be closed on Sunday night, so around 10 p.m. or 11 p.m. I think 10 p.m. So you need I think you can focus on Friday night or maybe Saturday if you would like, or maybe any day that you are available. And I think we can start with this partial fractions. Okay, so as I mentioned, that if we have a big chunk of fractions like this, x plus 5 over x squared plus x minus 2, we could simply factorize the denominator, okay, and then we could try to separate the fractions. Okay. So if you also taken my basic of math, I think I've explained this last week, but this is the idea is pretty simple actually. So we are going to separate the factors, and then because they both are linear, then we are imagining that they are a coefficient a and b on the top of the equation. And then our goal is finding the constant a and b. So we are going to find a and b by trying to combining these two, and then become this, and this divided with x minus 1 is x plus 2 divided by a. That is our first component. And the other one is we divide the multiplications with this x plus 2 is x minus 1, so ex minus 1. There are two ways to solve. We can just expand all the factors and then grouping all the component, like this is with variable x and then this is the whole constant, and we are equaling this to or we could let some x with becoming, for example, this is becoming 1 because this part will be 0, and then we can easily solve for a. And the other part is we let x equal -2, so we are getting the a is 0, component a is 0, so we could get to solve for b. Okay. And then after we get this, then we are going to write down, if we are taking the integral, then we could write this will be a is 2, so 2 over x minus 1 minus 1, right? So this is 1. And we can separate them, become 2 integral. Okay. Now, because we have this 2 separate integral, we could get the result directly. So x minus 1, we integrate. 1 over x minus 1 is ln. So this is 2 ln x minus 1. And then this part here is ln x plus 2. And this is plus c. We could, if you want, you could also maybe simplify this, but I think if you just end up till here, it's also already okay. Maybe you could move the 2 here if you want, or maybe this minus become ln like this. It's also okay. Okay, another example that might relate with this partial fraction is, let me give you integrations here. If we have x cubed plus x divided by x minus 1, so we have a cubic and divide by linear equations. And we know that both of this, the denominator and numerator, they are, we can say it's polynomials. The top equation, the numerator, is degree 3, like polynomial degree 3, and below that is degree 1. So we know the numerator, the degree is greater, right? So we could think this as in polynomial, this is, let's say, p over q. And when p degree is greater than q, then we could take these formulations become this, as in the polynomial's long divisions, if you remember. So if we take this, we could just, using the polynomial long division or syntactic division because it's linear equation, but I will just take the long divisions to make it more general, and then try to find out the results. So multiply is x cubed x squared, right? And then minus 0 minus x squared is plus x squared plus x. And then plus x. So x squared minus x. So minus again. So x minus x is 2x. Okay. And then this will be 2. So 2x minus 2. This is going to be, the remainder is 2. So we can write the equations. So this will be x squared plus x plus 2 over x minus 1. And if we integrate, it will be very simple, right? No need to worry about the integrations anymore now. So if we take these integrations, let me add the x. So we could take this 1 over 3 x cubed plus 1 over 2 x squared plus 2x plus 2 ln x minus 1, and then plus c. And I would like to give you some some descriptions on partial fractions, on what we are going to have, what cases we are going to experience. And I believe when you are getting familiar with the partial fractions, any integrations that it seems that we can do partial fractions, you will be able to solve it. But no matter simple or complicated the fractions, partial fraction always takes time, because we are going to like separate and then find the constant first and then do the integration. So maybe it takes time to find the constant to do the separations, the partial fractions. Okay, so in partial fractions, let's say we have this general P over Q. And we would like to express, okay, we would like to express as a sum of partial fractions. Okay, we are going to see that the expressions we are going to have like A over, let me write just with a general form or structure. We will see these forms. Okay. It means that A is a constant that we would like to find in the partial fraction, and the below that is our denominator, okay, that we are going to it has been decomposed or separated. Okay, so we could have AX plus B with power of something. It can be 1, 2, 3. Okay, but we still say that the denominator is linear. Okay? Generally, it's a linear with a factor of power. Okay, something 1, 2, 3. Okay. Or we are going to see that the expressions could have this expression. This is what we call irreducible quadratics. That is the quadratic equations that cannot be factorized. So we are just ends up with just quadratics. So when we have that, then the top equation will be less 1 degree than the denominator, which is the linear. Okay. And this will be true for all cases. Okay. And we are going to arrange what cases that we might to be aware of. Okay. I would like to give, at least we have three cases. And by these cases, again, for me, it's not important if you remember the case or not, as long as you are consistently know what you're doing. That's okay. That's okay. That's pretty much okay. Because when you solve, or maybe you simulate something with mathematical models, you don't really like remember your memories, right? So I think it's best to serve as just basic knowledge, and the rest is how you are adapt to that formulation or the logics, and then apply it to some other applications. Okay, let me start with the first case. So the first case we are going to see that this qx, we can separate, become different factors. So the first case is distinct factors, or no factors, no factor repeated. Okay, if you plan to take in the future the engineering of math, this partial fractions is still largely being used in those courses as well. Okay, so let's try to solve this. Okay. So I believe this should be take the compositions of the denominator. So let's try to factor. Okay, first of all, try to factor the denominator. So let's say we are a factor x like that. Okay, I think we have. And then we could factor this, try to factor. So this is 2x, x, and this will be 2 and minus 1, right? 4 minus 1 is 3, okay. So this will be having x, and then 2x minus 1, and then x plus 2, right? And perhaps we could write this without the integrations, and we concentrate on the partial fractions decompositions. Or maybe let me write the factors directly here. So x, 2x minus 1, and x plus 2. And the result here is nicely separated all the components on the denominator. So all nicely done. And the rest is just a constant on the top. And we could try to find out the result. And then this should be equal to x squared plus 2x minus 1. Okay. I believe you should be able to solve this. Okay. You should be able to solve this. Either you let the x equal minus 2 and let x equal half, and then calculate all the components here. But I think you still need to take the expansions. So you need to take the expansions. So you need to try to expand this, multiply all, and then grouping all the variables, equaling the left side with the right side. At the end, you will find the system of linear equations. Okay, that is what you get, and then solve that equations to find A, B, C. Okay, so I leave that to you, okay, to solve. And I believe when you have the constant, the integration will be also really easy integrations, right? Not really complicated one. So this is case 1. Okay, now case 2, this is when this px over qx, this ends up with the a1 like that, and ax b1, and then plus, and then you have the same exact denominator, ax plus b1, but with squared. And you say that this will be another constant a2. And then you have ax plus b1, it's cubed, well, if you would like to be precise, maybe this is a1x, a1x, a1x. But no, it's not really different. This is ar, a1x plus b1 with power of r. This is what we call the repeated linear factors. So we have the example. Okay, if we would like to decompose this x cubed minus x plus 1 over x squared x minus 1 cubed. Before we are getting the this so-called repeated linear factors, I would like to show you how we are going to be able to take this as long repeated linear factors. So if we just take these two small fractions here, so let's say we start by separating becomes these two. Okay, this is pretty simple to look, right? So x squared, we are going to have ax plus b here, right? And for the other part, this will be cx squared plus dx plus e. Okay, I think it's easy to follow. But now look at this. This part we can separate, become ax over x squared plus b over x squared, and this turns out to be a over x plus b over x squared. This is precisely the same thing as we have here. So we have something here, let's say this is x, and this other part is x squared. So we could say that if we have x squared on the left side, we could simply say that we could separate this x squared, become x and x squared with a constant on the top. Okay, so if you follow what I've been doing in below, then this is precisely what we get. And the same thing with the x minus 1 cubed. We will have a constant on the top, and then all the factors, they will be repeated with increasing in power. Okay, so this would be, let me write here, this will be a over x, okay, plus b over x squared, or let me write again here, x cubed minus x plus 1, this is x squared, x minus 1 cubed, and then plus, so we'll have another c constant, and we start from x minus 1, and then we will have another constant, and then this will be x minus 1 squared, and then we have another one which we are able to find, this is x minus 1 cubed, and this is the repeated linear factors. And how to solve and finding the ABCD, it's the same. Okay? So we need to equaling the left and right and find out the constant, and then substitute the constant, and then integrate the fractions. Okay, for A, B, C, I think it's easy to integrate. But for D, E, maybe we need some techniques. Okay, maybe substitutions or integration by parts. Okay, depends on the case. Well, you could try this and solve by yourself. Okay, we are going to have later maybe exercises. Okay? For the whole case 1, case 2, and case 3, we are going to focus on how to separate first. Okay? And then case 3, so when we have px over qx, this qx contain, so if qx contain x squared plus bx plus c, and then the b squared minus 4ac is less than 0, or we call this the determinant. So we call this part here, the quadratic, is the irreducible quadratics or factors. So if we have x, let me just get you the factors out. And then this will be a over x minus 2 plus bx plus c, x squared plus 1 plus dx plus e over x squared plus 4. And then we need to solve this. Okay? After we get the a, b, c, d, e, then we solve all the fractions. But I think to solve this part and this part, because we have the irreducible factors, sometimes we need to think on what kind of integrations that when we integrate the 1 over x squared plus 1, we are getting direct results. So we have, for example, if we take the 1 over 1 plus x squared and then integrate, this is also irreducible factors, right? What will be the results? The tangent, right? Tangent inverse. So tangent inverse x plus constant. So maybe we start from the derivative. Let's say we are going to have derivative of tangent inverse x over 2 like this. And what will the results will be? So 1 over, this is supposed to be x squared, but this is x over 2. So x squared over 4, right? And then we need to multiply the chain rule, 1 over 2 from x over 2, right? And then we rewrite this as 4 over 4 plus x squared. Okay. And then we are get to multiply by half. And we get that this is 2 over x squared plus 4. So when we have 1 over x squared plus 4, this will be equal to half of tangent inverse x over 2 plus constant. Okay. If we take derivative, we get this too, right? So if you take the integrations, we need to multiply by half. Or you could think that there's 2 here, and then you need to multiply by half to cancel the 2, right? Right? Okay. So, in general, you will get 1 over x squared plus a squared, and then dx, and this will equal to 1 over a tangent inverse x over a plus constant. So sum of the irreducible factors that we find, we can solve the integrations by taking it into the tangent inverse, okay, for some cases. So that's case 3. So case 3, we have the irreducible factors. Okay, the case 4 is similar to case 3, but it has repeated irreducible factors. So case 4, this is, we have repeated irreducible factors. So we will have a1x plus b1 over ax squared x squared plus bx plus c plus a2x plus b2 over ax squared plus bx plus c squared, and then plus plus let's say we are going to evaluate 1 minus x plus 2x squared minus x cubed Okay, if we take the partial fractions, so we will have x and then a and plus, now it's x squared plus 1, and the other one is x squared plus 1 but squared. So we will have bx plus c and dx plus e. Okay, maybe we can try to find this, okay? And then you can also try. So let's try to find, this is a, x squared plus 1 squared plus bx plus c, x squared plus 1, and then plus dx plus e, and then x. This will be x4 plus 2x squared plus 1, right? So we have ax to the power 4 plus 2ax squared and plus a. And this will be x cubed plus x. So we will have bx4 plus cx cubed plus bx squared plus cx. Plus dx squared plus ex. So we will have a plus b plus cx cubed plus 2a plus b plus d c plus e, and then plus a. This will be equal to this. Okay, and now we are equaling both sides. So we see that a, the constant, is equal to 1, right? So a equal 1, and c plus e for the variable x is equal to -1, and 2a plus b plus d is equal to 2, and a plus b, or c now, c is equal to -2. Oh, it's supposed to be in -1, sorry. Why is having -2 here? So this will be -1, and a plus b is 0. So a is 1, b becomes -1. So 2 minus 1 plus d is 2. So d will be 1, right? This will be -1 plus e is -1. So e is 0. So if we rewrite this integrations, this will be 1 over x dx. and then plus b is -1, c is -1. So we could write this will be negative x plus 1, right? Integrations like that. And then the dx plus e, d is 1, e is 0, so we will have plus x over x squared plus 1 squared dx. Okay, still not over yet. Okay, 1 over x is become ln x. And this part here, whenever you find this kind of fractions, we can separate again, right? We can separate again. So we are going to separate, become and then minus well, if you maybe doubtful, maybe making this bracket will help, okay, to see that it's actually becoming this negative. And then plus, let me still write x with x squared plus 1 squared dx. Okay, this part here, for x over x squared plus 1, we can take the substitutions. So let this one is u. So we are going to have ln, right? 1 over u. So half of ln x squared plus 1. Right? And then 1 over x squared plus 1 is tangent inverse x. And this part we can also substitute. So u is x squared plus 1, same thing. So we'll have a half in the front, but we are going to have 1 over u squared integrations. So this will be negative 1 over u, right? So we are going to have negative 1 over 2, and then 1 over x squared plus 1, and then plus constant. No. No, sorry. Yeah, so partial fractions is this just the process to separate, become small fractions, but still in all these fractions we need another method to solve. So it takes time. Okay, let's take a break. Okay. Now just some notes. Sometimes we are given some fractions that maybe we need to rearrange first before we do partial fractions. For example, if we take square root of x plus 4 over x dx. Okay, if we try our best to solve this, not sure on any other methods, but I believe if we take substitution, for example, the substitution for this x plus 4. So let the u is the square root of x plus 4. So if we take squared, this becomes x plus 4. Okay? So u squared, or maybe x, is u squared minus 4. So the whole thing for these equations and dx is become 2u, right? So this becomes integrations of u over u squared minus 4, and this will be 2u du. Okay. So this becomes 2, and the integrations u squared over u squared minus 4 du. And this part here, we could try to decompose the fractions because we can factor it, right? Or we could just divide and take long divisions. So take long divisions, so u squared divided by u squared minus 4, so 1. So we have 4. So we could take this and make it into 2 this will be 1 plus 4 over u squared minus 4 du. So this will be 2 integrations du plus 8, right? Integrations du over u squared minus 4. And I think you can solve this. Okay, you can solve this. And this part here will turns out to be ln, right? We can take some so we can take this into, this become 2u plus 8, 1 over 4 ln u minus 2, u plus 2 plus c. This is from partial fractions. We can factor this, right? So if you would like to know the process here, you could try by yourself here. Okay. And maybe before plus c, maybe we could exchange first the u with x. So this will be 2 squared of x plus 4 plus 2 ln, and then change all with x plus 4 minus 2 x plus 4 plus 2, and then plus constant. Maybe let me write here. Okay. U is equal to square root of x plus 4, you mean?
No. Yeah. Great.
Yes?
Yes.
Oh, why I'm writing 4? Should be 2. Yeah. Okay. Okay. So sometimes in the integration, one question maybe more than one technique to solve. Like maybe you need to rearrange first, and then partial fractions, and then you have different integration techniques. So in general, the partial fractions takes time because if it's not arranging well, then you need to arrange first, and then second, the partial fraction itself takes time to find constant, and then the third final step is to find out which techniques to be solved for each integration. So yeah. So given the partial fractions, and it's already have like combination of most of the chapter 7. Okay. Okay, now we move to the last section on chapter 7, which is the improper integral. Okay. We are going to discuss this for more exercise, I think, if not tomorrow, maybe next Wednesday. And I think, so today is 14, so maybe next Wednesday, if I am not in class, probably you will have quiz in class for 1 hour quiz. Yeah, I think it's with your TA, but offline quiz. Quiz is about chapter 6. So chapter 5, you're doing it online, and probably chapter 6 we are having next week. But maybe not in the early morning. Maybe you can get in class. We are going to start maybe around 9. I think it's helpful. I think it's helpful for you. Okay. Because I noticed that everybody say only half of the class. Yeah. Okay, let me go through. And actually, because we already in chapter 7 and almost finished, we still need just to have 2 sections in chapter 8, small sections. So I think by next week, I think we are finished. So we can have finals anytime. Okay, so I think 28 will be, well, let's say 28 is a final, or if I can get another room, maybe earlier, different day, but at least by next week I'll finish all the the content, the chapters. Okay, now let's start to get you to it's chapter 7.8. So we skip a lot in the middle. The middle part is there are strategy for integrations. I think we can focus on the just the exercise, and then integrating using technology. I think we can skip that part. And approximations. Yeah, only a few applied. So I think we can skip that as well. So this is, we call the improper integrals. Okay, what is improper? So what we have been done is what we call by a proper integral, which means, so let me write here. So far, we've done proper integral. So by proper, we define that the integrations, the definite integral from a, b of f of x dx, we assume that f defined on finite interval. And f is continuous. So this is the proper one. Okay. So the improper integral is when we have the interval is not finite, and maybe it also has discontinuity. Okay. So it seems that we are going to broke our own rule. We broke our own rule, but because we have some ways to overcome those rules, we still can try to, at least, let me just using the word approximately integration. But perhaps approximate is not really a good word. Well, we could say, because we have learned about limit, and we could get to the limit for the integral. Because the integrals might be getting the interval getting infinite, or it can be having discontinuity, which both of this can be related with limit. If you remember the limit. Okay, to start with, how this going to be described, let me just give you this part. Okay, let's say we have the 1 over x squared, and then we take the area, okay, under this curve from 1 to t, or we could take this a as integrations from 1 to t of 1 over x squared. We know 1 over x squared, if we integrate, this becomes negative 1 over x, right? So we take from 1 to t, and then we are going to have 1 minus 1 over t as a result, right? And then if we take, for example, the t, maybe we are going to change t into 2, 3, 4. We could see that from this graph here, if we take t is equal to, the area becomes half. If we take the t is 3, the area becomes 2 over 3, right? And if we take t equal 5, it's become 4 over 5. Now, if we let t getting larger and larger and larger, we are going to see that the area is going to be 1. Okay, because 1 over in limit infinite is 0, right? So we could say that when we take the limit as t getting larger of the at, then we could say that this will be equal 1, right? Now we could also rewrite this in terms of this integration here, which we call, this is the improper integral. So how to solve this is basically we take the limit and then take any variable that is, we can say it's like a dummy variable, and then write, or maybe let me write here, and then write this 1 and t. Okay. In general, if we still have this integration, we cannot really do directly integrate with this infinite. So we need to change this into our dummy variable. Let's say this is our dummy variable t. So we take the limit in front of this integration, take limit as t approach infinity, integration 1 to t. As we discovered previously that this part here, the integration, we can integrate. Okay, you can integrate become 1 minus 1 over t. And then we take limit, and then this will be the answer. So this will be equal to 1. Or maybe to be precise, this can be written as limit okay, to be complete, that is the solution. Okay, before we are going to look at the examples and what kind of improper integral that we might have, let me get you to another graphs that is, I think in our case here, going to be important. Okay, let's say we have this. Okay. So we know that when we have 1 over x squared, the area is finite. Okay, because we can find the area when we increase the t, right? When we increase the t to be infinite, the area is finite. Okay, but when we have this 1 over x, it says it's infinite. Okay. So let's see if we take the improper integral from 1 to infinity of 1 over x dx. We could say that this becomes, so let's take the dummy variable t, and 1 over x becomes ln, right? This becomes ln from 1 to t. And notice that we will have ln t and limit as t getting larger, getting infinite, of ln t is going to be infinite, right? So we say that this improper integral of 1 over x dx from 1 to infinite, this will be diverged or divergent. While its counterpart, the 1 over x squared, this is convergent. Okay. So the conclusions, okay, for this improper integral will always be only two, whether it's converge or diverge. Converge, it will converge to the finite number, okay, like finite area, or we could have an infinite area, or divergent. Now, if we look back to the definition for the proper, okay, that we assume that the function is defined on finite interval and the function is continuous. Okay? So the improper integral will be it's going to be having these two statements, but in a not correct way. Okay, for this proper, so we call it improper. So we will have type 1 for improper, that the interval will be infinite, that we have here, and function will have discontinuity. So this is type 2. So we have two. So let's describe all the types one by one. So type 1, let me describe in the new page. So type 1 for the improper integral, we call the infinite intervals. So this is if we have these integrations from a to t. So if this integration exists for every number that t is equal a or greater a, then if we take the t to the infinite, then we could write precisely what we have been done on the previous page. I need to provided that limit exists. Okay, and B, if we have the infinite is on the first endpoints. So this is t and b. If this is exists for every number that b is greater or equal to t, then oh, this is not t, sorry, should be negative infinity. And also provided that limit exists. And both of this a infinite f of x dx and negative infinite to b f of x dx, they are going to be convergent if limit exists and divergent if limit doesn't exist. And another statement that if both or let me write, maybe not B, let me write with A. This is for the next statement. If both converge, then if we can write, we can have also both endpoints are in infinite number. And how to solve this is basically we split up this two. Where A is real number, or maybe it's element of real number. Okay. Okay, last one for today's class is if we have this 1 over x with power of p, okay, dx, we would like to find the general rule to solve this. So let me write the limit for the infinite interval. Okay, and then we integrate as usual for 1 over x with power of p. So x is 1 minus p and 1 minus p. So we change the 1 over x with power of p becomes x with power of minus p. Okay, and we take the integration, so plus 1. Okay. And then let's factor out the constant. So p is a constant. And then plug in t. So t is 1 minus p like that. And then minus 1. And then still writing. And we can write this, take reciprocal, so t, p minus 1. Okay. And then still we have minus 1 here. And we can move this here, and this part will be equal to 0. So from 1 to infinity, 1 over x with power of p, this will relate to so if p is greater than 1, So p minus 1 is greater than 0. So we will have 1 over p minus 1. Okay. And if p is less equal 1, or p minus 1 is less than 0, so t, or let me write, this will equal to, or maybe let me write here. I think best way to write is the t1 minus p, as t getting larger, then t1 minus p also getting larger, which means that these integrations will be diverged. So it says that when p is positive and greater than 1, it's converged. So it's converged. And when p is equal 1 or less than 1, it's going to be diverged. As we see from integrations from 1 to infinity of 1 over x squared, this is converged, right? And 1 over x, which is p is equal 1, this will be diverged. I will stop until here. We are continuing tomorrow. Because there will be some student from Apply Foreign Language, I think they will take survey from the local student. But they are not here yet, so we can have a feedback time. Zoom out. Is it too small? Maybe here? Here, right? Okay, we can see tomorrow maybe some exercise from some example from here for this type 1, and then we can continue type 2 and another example. And if we still have time, move to chapter 8.
But if p is equal to 1, then it will be 1 over 0. Then
Okay.
I see.
Yeah, that works.
But I mean, like if p, because you write p is smaller and equal to 1.
1, yeah.
Then if p is equal to 1, then the front part will be 1 over 0.
Yeah.
So that will be like
Divergent. Still divergent. So equal, less 1 or equal 1 is also divergent. Okay, I think we can have our feedback. Have you joined? Okay. Okay. What's happened? Okay. Okay, I think we can start. 3, 2, 1, start. Sorry. It's trigonometric substitution. I hope you can try that out. Or you can check it calculator. But not sure. You can maybe you need to adjust the settings. I think you can adjust the settings for the calculators to be in fractions, not in decimal. Usually they will give you decimal, but I think it also depends on the calculator. Or you can go to the website, go to the Wolfram website. I have another website, but I forgot the name. It can also help you to compute some calculus. But let me look at that first. But the general website that I also frequently use is Wolfram. So whenever you have taken exercise, practice, you can always use that Wolfram Alpha. I believe it help you compute. So you're going to need the trigonometric substitutions. So you have constant plus t squared. So what will it be? I think it should be related to tangent and secant, right? You could check that out. Yeah, perhaps the time is too short. But try your best. You can try your best. Yeah, okay. I think I will use the calculators. What's the result of your calculator? Yeah, I think you need to read the instructions. Yeah. Sometimes in some calculators you need to put in the functions. They have set some manuals how to write the integrations and how to write the interval of the integration. Like you write in, I think in coding, yeah, you need to write in a linear sentence, right? Yeah, something like that. I think it depends on the calculators. So after this, there will be some survey for practical local students. I think still have few seconds. Use the double angle formula. Okay, I think we. Oh, 20. I think there's a ghost. Okay. Okay, who is San Elmo? Okay, okay. Who is integral? Okay. Okay. Okay, question 2. So substitutions. Yeah, try your. Okay, so then we'll give you a clue. It's substitute the cosine t. That's a clue. Substitute cosine t. And then use for the sine 2t, you could use the double angle. Become 2 sine t cosine t. And after that, you will be simplifying into more, more simple integration for integration by part. So you will have e with another component, and after that, you can do by parts. Oh, connections is slow, but only in this floor. The 5th floor, I rarely have this connection problem. Only the 4th floor. What is happening on the 4th floor? It seems that there is some dampener from echo.
I don't know, because cosine 0 is 0 and cosine pi is.
Oh! And don't forget to change the interval. Okay? Change the interval when you substitute. No. Okay. I confirm who is Elmo? Okay. Okay. Okay, there's some information I think for the survey. Yeah, please, you can start.